We begin solving this question by drawing a triangle. We will call the top vertex capital A, this vertex B, and this vertex C. Now recall that when you have an angle marked with capital A, then the side that is opposite of that angle would be marked as lowercase a. So this side will be lowercase a. Similarly, this side is lowercase b, and this is lowercase c. Now, we know that two of the sides of the triangle are going to be fixed lengths, 12 meters and 15 meters. We will arbitrarily call little a the 12 meters, and then little b would be the 15 meters. The question then speaks about an angle between those two sides. We're going to now call that angle theta. You can also call it uppercase C, but for our purposes, theta will be more useful. Now, let's write down some of the known information in addition to the lengths. We know that the angle is increasing at a rate of 2 degrees per minute. So we would express that in the following notation. We would say that the derivative of the angle with respect to time is equal to 2 degrees per minute. Now, at some moment, the angle between the fixed sides is 60 degrees. So we're going to say that theta is equal to 60 degrees. And then we ask ourselves, well, what is this question actually asking us to solve for? It says right here, how fast is the length of the third side increasing? So they're referring to C, that is the third side. That length is changing, and we're trying to figure out the rate of change of that third side. So in essence, we're looking for dc dt. This is our unknown. Now, the question gives us this hint. It says to use the law of cosines. And so let's write down that equation next. Here is the law of cosines, and we are going to differentiate it with respect to time. But perhaps before we do that, we should plug in the values of a and b, because those values are fixed. So they're not changing, they're constants in other words. Let's go ahead and plug them in for the a and b into the law of cosines. And then we can simplify it. We know that 12 squared plus 15 squared would be 369 minus, and then 2 times 12 times 15 is 360. Okay, this is looking really good. Now it's time for us to compute the derivative with respect to time. So when we do that, we're going to start out with the c squared here. We're going to use a power rule. So we're going to multiply the 2 times c. The exponent of 2 becomes just a 1 now, because you're subtracting 1. But we also must multiply by the derivative of c with respect to time. A lot of students forget to multiply by that extra dc dt when they're doing related rates problems. But please, after you do your power rule, you must also multiply by the derivative of c with respect to time. So that takes care of the left side. The derivative of a constant is 0 minus, and now we have the derivative of 360 cosine of theta. Now, hopefully we all remember that the derivative of cosine is negative sine of theta, but again, we have to make sure we also multiply by the derivative of our little inner function here. In this case, the derivative of theta with respect to time. So there is our derivative of the law of cosines function with respect to time. We can simplify it a bit. This 0 in front is negligible. We can see a negative times a negative would be a positive. That's pretty good. Now we are solving for dc dt, so let's divide both sides of the equation by 2c, so we can cancel it on the left-hand side. On the right-hand side, you're going to simplify. You have 360 divided by 2, so that'll become 180. Okay, so we're almost ready to plug in, but we have a couple of problems. Number one, we don't know the length of c, which we will be able to find in a moment. And then another problem is that theta was given in degrees. We're going to have to convert that into radians. Similarly, d theta dt was given in terms of degrees. We're going to have to convert that into radians per minute as well. So a lot of work to do here. Let's take an aside and do all of that work. Why don't we begin with the simple stuff? We can take theta, which was 60 degrees, and convert that into radians. Now remember, to convert degrees to radians, you multiply by pi over 180. And when you simplify that, you would get pi over 3. Let's next look at the value of d theta dt, which was 2 degrees per minute. And we want this in radians per minute. So it's a very similar idea. To convert from degrees into radians, we have to multiply by pi radians over 180 degrees. We do that, the degrees cancel. We are left with 2 pi over 180. If we reduce that By dividing top and bottom by 2, we get pi over 90. So that would now be in the correct unit of radians per minute. Excellent. We still have to solve for c, and to do that, we use the law of cosines, which we have just rewritten there. Let's go ahead and plug in the known values. Remember, we know the length, a and b. We also know the angle as well. That was the pi over 3 radians. Now, set your calculator to radian mode and type the entire right-hand side into it, and you get 189. And then if we square root both sides, we can see that the value of c is the square root of 189, which can be written as the square root of 9 times the square root of 21, which is equal to 3 times square root of 21. So now we have d theta dt, we have c, and we also figured out the theta. Let's go back and plug those three values into our dc dt equation here. There we have it. Now it's time to simplify. Perhaps we can begin with the sine of pi over 3. Remember, pi over 3 was 60 degrees. The sine of 60 degrees is root 3 over 2. And now it might be wise to continue simplifying the numerator a little bit. We can put the 180 over 1, and we can multiply all these denominators together, and then we can multiply all these numerators together as well. So if we multiply the numerators, we will end up with 180 pi root 3, and then that's all over 180. And that's convenient then, because those 180s will cancel in just a moment. Let's go ahead and cancel them now. And so this seems to leave us with just pi root 3 all over 3 root 21. And maybe to make it look a little nicer, we divide the top by root 3 and the bottom by root 3, because root 3 divided by root 3 is just 1, and then on the bottom you have root 21 divided by root 3, which is just root 7. So we are left with pi over 3 root 7. If you have a teacher who's very picky, then you might need to rationalize your denominator, so you can multiply the bottom by root 7 and the top by root 7. Holy smokes. Now in the top you have pi root 7, and then over 3 times root 49. But of course, root 49 is just 7. So the bottom is 3 times 7, which is just 21. So this would be a pretty good form here. And then you can approximate that by punching it into a calculator. You would get about 0.396. So this is the correct answer. Let us recall for units that we calculated dc dt. So for the units, we need a measurement of length divided by a measurement of time. And in this case, a measurement of length was given as meters, and the measurement of time was given in minutes. So meters per minute would be the correct unit for our answer.